Hello everyone. Today we're going to talk about backtracking algorithm. You may have been in some mazes that you are going to some path and you reach a dead end and you need to return back and try another way. So that's technique that we're using sometimes maybe in real world and games, which also is a useful approach to solve problems like for example end queens that we're going to talk about it today. So I'm gonna as I said, I'm gonna explain the end queen problems, and with that I'm gonna explain the backtracking approach. Okay, here I draw a four queens problem. That means that we have four queens, and the goal or the problem is to put these queens in the board on the like just 4x4 board, such that none of them attacking each other. Okay, so here also as you see, Q1, Q2, Q3, and Q4 all are all positioned in a place that none of them are attacking each other. So that's a solution for this problem. Okay, and we're gonna see that how using backtracking we can solve this problem. Okay. But before that, before going to the backtracking, we are going to see that if we are not using the backtracking, how we can solve this problem, and how many nodes, for example, or how many steps that we have to go through to find the solution. Okay. So let's say that we are creating a tree of the states of the problem. Okay. So at first we are starting with an empty. Okay, with an empty board. Okay, the board is empty. It means that there's no queen on the board. Then, let's say that we are placing the queen number one. I'm just writing number one. Okay, at column one. Okay, so at each step, okay, we are putting a queen in one row. Okay, so queen, so the first number is queen and the second row is the column. Okay, so we are putting the first column, okay, the first queen. Then we are going to the next row. Okay, the next row, and we're going to put the second queen. So I'm putting the second queen, okay, and I'm putting in the first column again. Okay, but if I put the second queen on the same on the first column, okay, because queen one was already on the column one, okay, so it's gonna be an attack to quick one, so that's not gonna end to the solution. Okay, but we're gonna see that how it will go. Also, let's say that here at first I put the queen one at column one, but what if I put the queen one on column 2, such that what I have put in my in the drawing here, I put the queen 1 in column 2. So here again I can put the queen 2 at column 1. Okay, so it means that I put it here. Okay, but again it's not the solution, because it's not appropriate, because they are attacking each other. Okay, so that's not the good option. So let's see that based on things that we have drawn so far, let's see that how many the nodes we will have in this tree. Okay, so the first row I have one node. Okay, so one node here. Here the second row I have four nodes, and why? Because I can put queen 1 in also the third column, and also I can put the first queen in the fourth column. Okay, so as you see on the second level, okay, I have 4 nodes. Okay, and here for the third row here, okay, I also, for every node it's possible to put the queen in every node that I have. Okay, so 4 nodes for this one, 4 nodes for this one, 4 nodes for this one, and 4 nodes for this one. That's gonna be 16. Okay, or here that is equal to n to the power 2. this is n to the power 1. And definitely for the each node of here also is gonna go 4, also 4, and also rest. Okay, so here if I have this one, then it also goes 4. Here gonna be n to the power 3, that's gonna be 64 nodes. Okay, the thing is that I can put the first queen here. Okay, so I have n ways to put here. I have the n other ways to put the queen here. Also I have like n columns to put the queen here, and also n here. Okay, and so together, because I have this is n queen and I have like this n rows. Okay, so it's gonna be n to the n gonna be the number of nodes that I'm gonna have. Okay, so the n to the n is the number of like the ways that I can like put these queens in this board. Okay, so and let's see that what gonna be the number of nodes in this tree. So number of nodes gonna be 1 plus n squared plus n cubed and plus n to the power n. And n to the power n, as I said, is the number of leaves that we have. So if we sum these numbers together, then they will be equal to n to the n plus 1 minus 1 divided by n minus 1. So that's the number of nodes, okay, that like we are going to create for this n queen problem. Okay, so and like the possible solution that we can create out of these like trees. So let's say that and a solution is a path from the path from the root here to some leaf, some leaf. Okay, so for example, you are saying that here putting the first queen in the second row, then putting this second column in column 4, as put the third queen in column 1, and then put the queen 4 on the third column. That's going to be solution. Okay, so also that's a path from the tree to the leaf of the node. Okay, where Q4 and 3. So here, if we go, we'll have 4 and 3 is the leaf node, and it has some parents. Okay, so together it's going to be solution. We call the possible solution in state space tree. Okay, so that's the possible solution that we can have this tree. Okay, so and we call, as I said, we call it state space tree. Okay, so but as you see, this is not the this takes a long time. Okay, and the number of like the state space tree is a big tree. Okay, the number of nodes is this number, n to the power n plus 1 minus 1 divided by n minus 1. And the number of leaves node is equal to n to the power n. That is a big number. And like assume that n is 16, and 16 over 16 is a big number. Or I don't know, 17 is going to be a very big number. Okay, so we're going to like to find a better solution for that. But even in the like the this solution, we can see that we can just optimize our solution. Okay, so our goal is to find the solution first. Okay, and then we can see if we can optimize it or make it better. Okay, so our next video, I'm going to talk about how we can improve this solution. So as we said, the number of nodes were 1 plus n squared plus n cubed until n to the power n. Okay, but the thing is that when you're putting a queen in one row, you cannot put another queen in the same column. Okay, so it means that in your tree you can remove some nodes that you know that they're not gonna give you a solution. Okay, so what happens is that at the first row we'll have this like n, so you can put the queen in any of the columns, okay. But for the second one, okay, for every for every queen, so you cannot put them in the just you cannot put in the column that is already being occupied with the first queen. So you have to put in another one. So the number of nodes will be n divided by n minus 1. And n is the number of queen, and n minus 1 is the number of columns that remain. And definitely for the next one, because the number of columns is n minus 1, and now the third column you are removing 2 columns, so you cannot put the queen in the previous 2 columns. So it's gonna be n divided multiplied by n minus 1 plus n minus 2. Okay. So, and at the end, you will have, if you like just to sum all the values, all the nodes, the number of nodes together, it's going to be 1 plus n plus n multiplied by n minus 1 plus n multiplied by n minus 1. Multiplied by n minus 2, and at the end it's going to be n multiplied by n minus 1, n minus 2. That will be n factorial. Okay, so that's going to be the total number of items that's gonna we have. So that's going to be an upper bound on the total number of nodes. There's going to be exact number of nodes I will have in the tree. Okay, but now we removed some nodes from the tree, okay, because we already know that there is no way that these 2 queens can be also on the same column. No, not on the same column, also not on the same row, okay. And also we'll have this condition that no 2 queens should be on the same diagonal, okay. On the left diagonal or the right diagonal, okay. 2 queens cannot be on the same diagonal, okay. So next we're gonna continue on talking about solving the n-queen problem using backtracking approach.